So this is joint work with a few people. There's myself, there's Thomas Forsdyke, who is an undergraduate student in our lab at Carleton University. Shashank Pant is at the National Research Council in Pascale, Sevigny, and Bhashyam Balaji are with DRDC in Ottawa. And Sreeraman Rajan, who's actually in the audience back there, is my supervisor. So he runs the lab. So the idea of this work is that we want to improve a state-of-the-art method for detecting moving targets in real time. So constant false alarm rate detectors are the standard class of detectors used for this problem. I'm going to explain how those work shortly. But basically, whenever you're working in real-time target detection, you see CFAR algorithms come up. And we're using a pre-processing step, which involves a method called dynamic mode decomposition. So this is a kind of dimensionality reduction algorithm, right? You have some multi-dimensional, like complicated data. You want to reduce it to a few parameters that describe the data pretty well. So we use this as a pre-processing step in our algorithm to reduce noise and clutter in the data set. So first you do that, and then you apply CFAR. And hopefully this will improve the performance of the detector. And we found that it did. So I'm going to be talking about both of these concepts, CFAR and DMD, and how we combine them to produce this so-called DMD CFAR algorithm for target detection. So first, I'll describe constant false alarm rate detection. So this is a class of adaptive algorithms for real-time target detection, as I said, and it uses a moving window. So the idea is that if your data is coming in at real time, your detector isn't going to be able to see all the data at once. It's going to be able to see chunks of the data at a time. So the way you model this is you have this moving window. And this window consists of three things. There's a cell under test, right? That's the current cell that it's looking at. And it's going to calculate some threshold for that current cell. And then there are window cells and guard cells. So as you can see, the cell under test right here is surrounded by guard cells typically. The purpose of the guard cells is just that if you have a target in the cell under test, sometimes the target bleeds out a bit into the surrounding cells. So for statistical reasons, you want to sort of cordon that off. And the window cells are where you're actually looking at the values in the cells to compute your threshold. And by values, I typically mean radar amplitudes. Those are often used. So you're looking at some statistic of those values. And based on that statistic and some formulas which you derive, you're computing a threshold. And if you score above that threshold, you say target detected at that cell. And if you score below, there's no target detected at that cell. So that's how it works. Now, an important component of CFAR algorithms is first, you want to set a parameter, which is your desired probability of false alarm. The reason it's called constant false alarm rate is that you say, I want a probability of false alarm of less than 5%, say. And then the detector's job is to produce detections with a probability of false alarm, like an empirical one that actually is less than 5%. So there's that parameter in the code. And another thing that you should know about them is that the threshold formulas, they're like classical formulas for these for a variety of like classical radar settings. And these formulas are derived on the basis of assumptions about the background noise. So typically you assume like independently and identically distributed complex white Gaussian noise, and then it passes through like a square law detector or something, and you might get like a Rayleigh distribution. This is how CFAR theory works. So that's what that is. Oh, and actually I should say one more thing about this. There are like two major categories of CFAR. There's cell averaging CFAR, where typically you're looking at like the mean of the window cell values. And then there's ordered statistics CFAR, where you're looking at the median or some other like percentile cutoff. You're computing that statistic. So we focused on a comparison with cell averaging CFAR in this work, but more recently we've extended it to a comparison with other forms of CFAR. I'll talk about that a bit at the end. So the second major technique here was dynamic mode decomposition. And this was developed like around over a decade now ago, but it hasn't been used in exactly this way. So dynamic mode decomposition, the idea is you have some time series data, possibly multidimensional, and you're trying to model the time evolution of this data from time step to time step by a linear approximation. So you might have two vectors that describe like sets of consecutive time steps, and you have some linear operator that at least approximately moves from one set to the next. And you could do this, you could calculate that kind of approximation by like forming these column vectors into two matrices, and then like this is your linear operator. You can take the pseudo inverse, but that's computationally expensive, especially when you're working with some huge data set. So basically, what you need to know about this algorithm is it instead uses a singular value decomposition in a certain way to solve this problem. And this produces so-called DMD modes and DMD eigenvalues. And these are basically like a low rank approximation to the evolution of your system, where the modes are sort of analogous to like the modes you might get in a principal component analysis, except they're not necessarily orthogonal. And the eigenvalues basically describe the time evolution. So there you have like growth and decay rates, and you have frequencies. So that's why sometimes you hear the slogan that DMD is like a principal orthogonal decomposition, which is basically the matrix decomposition for PCA, together with Fourier analysis. So how do we combine these two techniques? Well, let's say you have a video of a moving target consisting of range Doppler frames. So the x-axis is range, the y-axis is Doppler in Hertz. You have this visualization of this moving target. What we do is we take a certain number of successive range Doppler frames, call that R, and we use those to make these matrices V and V prime that you saw in the dynamic mode decomposition on the previous slide. So we're taking a huge amount of data, I mean, several frames that might have like 1,000 by 1,000 cells in each frame. And we're making these giant vectors, and those are those vectors V and V prime. And then we're trying to figure out the linear operator that like approximately describes the transition between these vectors. So we can compute a low rank reconstruction, which is basically a portion of the range Doppler frame that can be expressed by the low frequency modes in the dynamic mode decomposition, right? It gives you those like eigenvalues, and those have frequencies. And the low frequency modes, what they capture is something that moves very, very slowly. So there you're going to see like static clutter. You're going to see like noise that doesn't change much over time. If you have something very slow moving, like an object or something, you might capture that as well. So that's the method we used. So you subtract that away, and then you get some sparse residual. You take the magnitude, and then you have some magnitude map that like hopefully shows your moving target more clearly. And finally, you apply CFAR, in our case, cell averaging CFAR to that magnitude map. So an example, you can see some clutter here before DMD, and you can see it clears up the clutter a bit, right? You don't have these like large peaks on the clutter graph anymore. So this is just a simple example for how this technique can be used to clear up data. I was asked by one of the reviewers about the time complexity, so I looked into this. So if you suppose that there are n range Doppler bins per frame, and you have a sliding window of length r, and you've processed like k frames total, then if you ignore the cost of like the fast Fourier transform step that's just used to generate the range Doppler in the first place, which is shared by both algorithms, the time complexity of that should say CA-CFAR, it's going to be big O of k, the number of frames processed, times n, the number of range Doppler bins per frame. And that's like if you really optimize the algorithm. And then the time complexity of DMD CFAR is going to be something larger than that. So there are three terms there. But the important thing to notice is that first term, the big O of k n r squared, is really going to be the dominant one in practice, because usually you'll have like a ton of range Doppler bins. Like I said, it might be 1,000 by 1,000 or something per frame. And you might have like 3 of these consecutive sliding windows that you're taking for the DMD. So generally n is much greater than r. So the leading term dominates, and basically you get big O of k n r squared. So this is going to be slower than CA-CFAR by a factor of like approximately r squared, where r is the number of consecutive frames that you take for the DMD. So this is an example of the sort of results that we got. This is taken directly from our paper. So at varying SNRs, we looked at the probability of detection and probability of false alarm for both cell averaging CFAR, just the standard algorithm, and DMD CFAR, and we did find an improvement. The improvement for probability of detection, you can see a slight increase there from 0.278 to 0.389. here from 0.722 to 0.889. Otherwise, it was the same. The less than 10 to the minus 4 is just where our codes like gave us 0.0000 or something. So practically perfect for our applications. And the probability of false alarm just consistently improved on the DMD CFAR side. So we've calculated much more data of this sort since submitting this paper with a variety of different variations on this algorithm. And I'll show you some visualizations. So this is the probability of detection, just the data you saw on the previous slide. You can see it's sometimes they're equal. When they're not equal, DMD is better. Probability of false alarm. Yeah, DMD is better as well. You want a lower probability of false alarm for fixed SNR. So I'm going to talk a bit about more recent approaches that we've taken to this line of work, because we've extended it in some ways since writing this paper. So one thing that I noticed when thinking about the way this algorithm works is DMD was developed originally to avoid taking a pseudo inverse, right? You have like V equals AV prime, right? Some matrices and vectors. And you could just take the pseudo inverse of A and that would solve your problem, but it's very computationally expensive. But our algorithm actually ends up taking a pseudo inverse anyway, albeit of a smaller matrix. So there's a step when you're doing the low rank reconstruction that involves the pseudo inverse of a matrix, but it's just a matrix consisting of a subset of all the DMD modes that have sufficiently low frequency for their corresponding eigenvalues. So that's a much smaller matrix. So for example, we were often working with like a rank of 3. So you have 3 DMD modes. And then you take a subset of those. So you have less than 3 potentially of these entries. And that's obviously much smaller than like, these like 1000 by 1000 data matrices where we would be taking the pseudo inverse if we were just doing the naive thing. But I was curious how much like, what if you just use the pseudo inverse instead of doing DMD? And it turns out you can optimize it in such a way that you actually get a slight improvement in the constant of the algorithm. However, you're still going to get like it's still going to be worse than CA-CFAR by a factor of R squared. However, I then found a better approach. So it turns out I was watching a talk by like one of the creators of dynamic mode decomposition. I think it was like Nathan Katz. And he was saying that now there are these novel variants of DMD called optimized DMD and bagging optimized DMD, or BOP DMD and OP DMD. So we just tried those out because he was basically recommending that these algorithms should always be used instead of DMD. DMD sometimes runs into pathologies, and these algorithms are just strictly better in those cases. So I tested these, right? I generated like OP-DMD CFAR and DMD CFAR, and I found that OP-DMD is slightly better than ordinary DMD for this, and BOP-DMD is strictly better than DMD and OP-DMD on all tests. So I just recommend doing this with BOP-DMD now. And in fact, it was also better than OS-CFAR, which I tried, right, using a median. And it was also even slightly better than what's called VI-CFAR, or variability index CFAR, which is sort of a clever combined algorithm that sometimes it uses cell averaging and sometimes it takes like greatest of or smallest of, depending on the case. Okay, so that's all I wanted to say about this. Thanks for listening.